Okay, so now I want to talk a little bit about experimental designs and causation. So this is an important topic because there's only one way we can determine the true cause and effect relation between a predictor and an outcome variable, and that's through an experimental design. And actually, it's through a randomized controlled experimental design. So that's the ideal. But let's go through this step by step and with a lot of examples. And in the end, I'll have an exercise for you all to do, and we'll talk more about that when I get there. So let's start with experimental designs. If you think about the function of an experiment, experiments are designed to determine cause and effect. So there are two sets of variables in an experiment. Well, there are two variables in an experiment. There's the independent variable. The independent variable is the variable that the researcher controls. So in an experiment, it's a treatment generally. So one is being assigned to the different levels of the treatment by the experimenter. So the experimenter has control of the independent variable. And then you have the dependent variable. So the dependent variable really is the variable of interest. So it's the one that we're trying to change. So we'd like to see change due to the manipulation of the independent variable. So it's your outcome, you may also call it a criterion variable, whatever the outcome of interest is. It can differ depending on the level of the independent variable. That's really important. So what I mean by level is some variables are continuous variables, some variables are categorical. So a categorical variable would be something like an individual's biological sex, because there's categories. And a continuous variable would be something like driving speed. So I'll talk more about this when we get into statistics. So I'm not going to really spend a lot of time right here, but the different type of dependent variable will determine the type of statistical analysis you could do. You use different analyses depending on whether your variable's continuous or categorical. Internal validity is a special outcome that we seek when we do experiments. And we can say that a study has internal validity when we can conclude without any doubt that the effect that we see of the change that we see in the dependent variable is caused by the independent variable and no other variable at all. So that's why we do experiments, because we want to see if the changes that we see in our dependent variable are due to the independent variable. So for instance, if there's a drug designed to slow or to cure somebody from the coronavirus disease, so that we'd hope that it's that drug that changes the outcome and nothing else in the environment or nothing else at all. This is important because it introduces the idea of confounding. So confounding occurs when we call this the third variable problem, when there are other variables that compete as causes of the change we observed in our dependent variable. So often other factors, and one of the main factors of all is something called expectation, especially in drug trials. So these other factors can interfere, right? So they can occlude the situation. So we think that our experimental manipulation is what's causing the change in the dependent variable, but in reality, it's these other factors. An example of a confound that we expect in an experimental design in a drug study would be, say, if I created a drug, I call it sunshine pills, right? Sunshine pills that supposed to make people happy, and I give my sunshine pills to people and they get happier. So that's good. So I think that it's the sunshine pills that are causing the change in their level of happiness. However, it could also be expectation. So if you ever gone to a health food store, gone to a health food store, you've seen all these nutritional supplements that make all kinds of claims. So the creators of them, or the businesses that created them, have all these claims for everything, like it can cure everything. Well, a lot of times people feel better when they take these supplements. Well, the reason they feel better is because they expect to feel better. Expectation is a key confound in experimental studies of treatments, particularly with drugs. So we actually have to control for the effect of expectation in drug trials by giving individuals a placebo and randomly assigning individuals to a placebo group versus an experimental group. A placebo is an inert substance like a sugar pill, or if there's an injection, it's saline. It's something that has no effect at all. If people do as well in the placebo group as they do in the sunshine pill group, that means the sunshine pills really do not do anything. For us to conclude that the sunshine pills are better than the placebo, they'd actually have to do above and beyond, or generate more happiness above and beyond that which is being generated by the placebo. So that difference between the placebo level of happiness and the sunshine pill level of happiness is actually the area of improvement. So we always have to control for confounds. In experimental designs, one way to control for confounding variables is through a factorial design. So factorial designs occur when we have more than one independent variable and a dependent variable. So our variables have to be categorical our independent variables are categorical. For instance, like you could have whatever the treatment is. So say you're assigned to the sunshine pills group or the placebo group. So that's controlling for placebo, right? So there's two levels there. If we just have one independent variable and nothing else, just test its effects on the dependent variable happiness, we could actually call that a one-way design. But we could add another control variable. Say we expect that there may be differences between males and females and the effects of the sunshine pills on happiness. So we want to control for a person's sex. So we then would have another independent variable. This would be called a two-way design. So there's two independent variables. So one of them would be biological sex, and the other one would be the sunshine pills treatment. Now, we can also just call it an n-way design, where n is the number of independent variables. So we could have more than two independent variables. The only problem with more than two independent variables is that you could actually run into some issues there, because the more independent variables you have, the more complicated the design is. I'll show you in a moment what I mean by that and why that's problematic. So that's what's called a factorial design, right? That's what's called a factorial design. Factorial designs are really great because they allow for us to test for moderation. Moderation is an interaction effect. So what I talked about, let me step back a second. So confounding variables can either be moderators or mediators. So if I believe that sex is a person's biological sex is a confounding variable in the relation between sunshine pills and happiness, then I can actually test the effect of sex, whether sex moderates the relation between the two. What I mean by moderation is then what that means is that the effect of the sunshine pills and happiness for males would differ from the effects of the sunshine pills and happiness for females. So that's what's called a moderated effect. So we would say that sex is an effect moderator because it moderates the effect of the independent variable on the dependent variable. So there's different effects for males and females. That's what I mean by moderation. So factorial designs allow us to test for that. I also mentioned that you could have the confounding variable could be a mediator, and we'll talk about that in a second. By the way, a confounding variable is a variable that's related both to the independent variable and the dependent variable. So we always have to take that into account. You always have to account for confounding variables. Okay, so here's an example. Let me see if I can make sure that you can see this clearly. Here's an example of a factorial design with two independent variables. So you could say that this is the sunshine pills treatment and control, and this is some other variable, because there's three levels, so it can't be biological sex, but it could be something like racial, ethnic group. So you can have white, black, and other. So you can have three different groups here. So you'll notice that there are cells here. There's 6 cells because there's two groups for the treatment and 3 groups for race/ethnicity. So 3 times 2 is 6. So there's going to be 6 cells here. There's values out here on the periphery, and there's values out here on the periphery. These are actually called marginal mean values. So if I wanted to test if my independent variable has an effect on the dependent variable, I can forget completely about these different levels of variable A, like the different race groups, and I can just test to see if the mean, the overall mean for B1 differs from the mean of B2. If they do differ, I would say the independent variable B has a main effect on our dependent variable. By the way, when it says mean, these are the means of my dependent variable. So this would be mean happiness, mean happiness. All these cell values here are the mean of happiness for the different groups. I could also do the same for independent variable A. I could say, is there a difference in happiness for race? So I ignore all the values in the cells here, and I ignore the treatment completely, and I just focus on race, and I can see if the means differ by race group, means of happiness. But because I'm interested in controlling for confounding variables, I'm really interested in what's within these cells. So I might want to see if the effect of the treatment on the outcome differs by one's race. So now this is where I'm looking at what's actually within these cells. So this is a 2x3 design, and I'd mentioned, yeah, if we have more than 2 independent variables, things can get kind of dicey. The reason is because each of these combinations, like B1A1, B1A2, have to have people in them, right? The more independent variables, first of all, this is 2 dimensions. You know, I can go to 3 dimensions, 4 dimensions. You can't visualize them anymore, but all those cells have to have individuals in them. The more cells I have, the fewer individuals I'll have within each cell, and that makes the statistics a little dicey. So we don't really want to do that. The important thing is to think through your design before you get started. And let's see what else. Oh, in terms of an interaction, so an interaction, when I talk about interaction, I'm talking about moderation, and I already defined that for you. And I'm going to get back with an example. But the telltale sign of an interaction is a crossing of lines in a figure, because we always have figures associated with interactions. And those figures are actually the easiest way to look at an interaction effect, or to test for an interaction effect, besides statistical analysis. So here's an example. We have, does caffeine consumption influence driving performance? Well, most of you would think, yeah, sure it does. You know, if I drink a lot of coffee, I'll be more alert. Some of you may say, if I drink too much coffee, I'll be jittery and I won't drive that well. So that's a good question then. So another question was, does the effect, if any, differ based on sleep deprivation? So there's 2 questions here, right? So it's caffeine consumption and sleep deprivation, meaning that we have 2 independent variables, right? So we break this down into caffeine consumption. There's low, medium, and high consumption. Sleep deprivation, there's not deprived and deprived. So we can look at main effects again. We can, for each of these, like for instance, does sleep deprivation improve driving performance? So our dependent variable here is a measure of driving performance. Driving performance, higher scores mean better performance. So just on the surface of it, it looks like sleep deprivation, not being deprived, improves driving performance, which we'd expect over the deprived. We'd have to test this statistically to see if there's a significant relation. By the way, the larger your sample size, the more likely you are to have a significant effect. That's just the way statistics go. In terms of caffeine consumption overall, so let's just assume that we have these and they are statistically significant. Just for the sake of argument, we'd say sleep deprivation has a main effect on driving performance, and so does caffeine consumption, with medium levels of consumption leading to the best performance, followed by high levels and the lowest level. So that would make sense to us. Like if you drink too much coffee, probably have to stop to go to the bathroom every 5 minutes anyway, so that's not a good thing. It's not going to help your driving performance. Here is what I mean by a, let me make this a little smaller. Okay, this is what I mean by a crossing of the lines. So the question was, is there a main effect for caffeine consumption? Is there a main effect for sleep deprivation? Well, we already answered that question. Now we wanted to know, does the effect of caffeine consumption on driving performance differ for levels of sleep deprivation? So we have two levels of sleep deprivation, not deprived and deprived. So when we look at this figure, first of all, we see that they cross. So that's already telling us that there's going to be an interaction. So there's a crossing of lines. By the way, sometimes these lines can cross outside of the boundaries of your study too. So we're looking at this, and what this figure tells us is that among those who are not deprived of sleep deprivation, a medium level of caffeine consumption is best. However, among those who are sleep deprived, it seems like a high level of consumption is best. Although you'll notice that there's a difference in the slopes. It's losing a little bit of its effect, but it's still pretty good. So this is an example where sleep deprivation moderated the effect of caffeine consumption on driving performance. Now, confounding variables can also be mediators. So mediator is a special type of effect. So in this case, a mediator is kind of an intermediate variable. And here's an example of a mediation effect. So, and I remember getting this, I forgot why, there was a study I was thinking of with one of my students of doing, and I think this is why we were looking at, I use this example. So here's the example: the effects of an athlete's time commitment on her sport and academic performance. So that was what we were interested in. So we were interested to see if there's a direct effect. So when I talk about direct and indirect effects, the direct effects is just an effect from the predictor. It's like a main effect, the effect from a predictor to an outcome. So does an athlete's time commitment to her sport impact her academic performance? That's the question here. An indirect effect would mean that if it does, there might be some intermediate variable. So in this example, I have the effects of an athlete's time commitment to her sport on her academic performance is mediated by perceived loss of control. So if an athlete is too involved in her sport, she probably feels like she has less control over her time, and that could influence her academic performance. So there's a pathway that's the effect is of the predictor on the outcome is channeled through the intermediate variable. Now, so the mediator variable here, this control, is actually a confounding variable because it's related to both academic performance and one's time commitment to her sport. We could also include a moderator, and you get what's known as moderated mediation. So these things can get really, really complicated, and that's the nature of the world. Like, for instance, I'm doing a talk today on implicit racial bias, and I was asked to look at whether implicit racial bias from physicians and other healthcare practitioners affect health disparities. So we see a lot of health disparities by race, and I was saying, there is no direct effect based on the literature. However, the effect is probably very complicated, so it's channeled through a lot of processes, like, for instance, trust, patient trust, patient compliance, patient understanding of the instructions, etc. So the relation is probably very, very complicated, and that's the way most things are in life. They're not very simple. But simple is always best. Remember that when you conduct an exam. If you can find a simple direct effect, you're always pretty good, in good shape there, okay? So in this case, I was saying perhaps there's moderation occurring, like the moderator could be something like coach support. So for among athletes who have a lot of coach support, the effect of time commitment on academic performance may still occur through perceived control, but it may be different than the effect among those who have no coach support. So there's probably a difference in effect. One may be significant, one may not be significant, but there's probably a difference in effect. So that would be an example of moderated mediation. So you always have to rule out all of these. One rule I have is there's always heterogeneity. So there's always some kind of a moderator somewhere. So you always got to rule that out. All right, let's talk a little bit about judging causation, because our interest here is causation. By the way, in these mediation studies, unless we have an experimental design, you cannot conclude causation. Now, we can include as many confounding variables or control. We call it control. We can control for as many confounding variables as we like, but it's really hard to conclude causation because we're not having an experimental manipulation in most of these studies. In fact, most of the studies that are done using mediation are not experimental studies. They're just what we call observational studies or non-experimental studies. So we're just collecting data somehow, maybe through surveys, or we're using archival data, and we're running these tests, these hypotheses. So we cannot determine causation in those studies. And you can control for variables. It doesn't have to be in this factorial design that I showed you that you can do in an experiment, but you can also control for these other variables statistically. And that means if we include them in our statistical models, whatever those models may be, like regression or something like that, we can actually control for their effects. We can statistically control them. What we do is we hold them constant for everybody. It means everybody gets the same level of the control variable. So if we're controlling for, say, something like, coach support, everybody would have the same level of coach support. We'll talk more about that in statistics. In terms of guidelines for judging causation, first important one is temporal relation. So you can, in a study that's, say, a cohort study design, even though it's not experimental, you can meet one of these criteria if you have the correct temporal association. If the putative cause precedes the effect, that's a good argument in your case, right? So if getting vaccinated results in not getting the flu, we could argue that the vaccination was responsible for one not getting the flu because the vaccination preceded the flu. Or somebody didn't get vaccinated and they got the flu. So the not getting vaccinated precedes the flu. Strength of association. The stronger the association is more indicative of a plausible causation. Again, so this is important because people confound correlation with causation. Correlation means that two variables are related, but that doesn't mean that they're causally related. But a strong correlation suggests a possible causal relation, which needs further investigation. Dose-response relation. A higher dose means a greater effect. And I give an example here. For the greater the minutes of exercise, the greater the happiness. So that's a dose response. So we think the same with medications. Like I had to take two ibuprofen for something. If I took one, it wouldn't work as well as taking two. So there's a dose-response relation in terms of reducing pain. Replication of finding science requires replication. Replication is not sexy in the research world, so that's sad. People want to find these really novel, cool things, and those are what get published, often the novel findings, but the ones that are more important are the replication. So maybe you didn't find the special thing, but so that person gets all the praise and all the media coverage, but that special finding may be false, right? May be false. So therefore we require replication. We want to see that finding again with a different sample, but there's a bias toward novel findings in terms of publication. Biologic plausibility. Is there a plausible biologic cause or pathway for the relation we've seen? So for instance, exercise increases with exercise and happiness. exercise increases the release of dopamine, which is rewarding, which can then make a person happy. So there's a biologic cause there, a plausible biologic cause. Consideration of alternative explanations. If you've ever attempted to publish a study or write a grant or something, you would know this right away, that unless you account for all other competing explanations, you may not get your manuscript published. So you always should say, even though A is proposed to cause B, it's possible that B could cause A. You always have to account for that. Cessation of exposure. Removing the exposure removes the effect. So, like, for instance, if a horrible study would be like exposing somebody to exhaust from a car, and then they start coughing. This was actually, believe it or not, in terms of IRB and institutional review boards, this was actually done, I think, by Mercedes or somebody recently. So it's an example of unethical research exposing individuals to exhaust. But if you remove the exposure, then the effect should go away. So cessation of exposure is another criteria. Consistency with other knowledge. Yes, it should be consistent, so it shouldn't be out of the blue, and there's nothing else that would even be similar to it. An example is distracted driving is related to automobile accidents. Well, that's plausible because we also know that there are limitations to working memory. That's the stuff that's in your mind at this very moment, nothing else. So if it's overloaded, it's really difficult to concentrate. Does that make sense? And the specificity of the association, so the factors associated with only one disease. A good example of this is this belief that this suicides that we see among National Football League players who are retired are caused by concussions. Well, that's actually not a necessarily or blows to the head, I should say. That's not necessarily the specific association, because you could have other factors that cause suicide, including the CTE or mild cognitive impairments or depression, etc. There's so many other factors that could be associated with suicide. So there's no specificity of the association. All right, let's talk about steps for conducting an experiment. So this is something that you should focus on, because in the end, when you have to do your capstone, you need to know how to do this, because we're not doing an experiment, but we are doing a study design that follows a similar approach. But in your grant writing course, you are doing an experiment, so you really need to know this. So first thing you do is write out your research question. You start by operationalizing your independent variable and dependent variable. What I mean by operationalize, tell me exactly how you're going to measure it. Like, the independent variable is random assignment to this drug, to the sunshine pills, and to the placebo, which in this case will be a sugar pill. So very specific. And a dependent variable is happiness, which will be measured by the Rodriguez happiness scale or something like that. And very specific. Write out your hypotheses. So we haven't taken stats yet, but probably somewhere in your history you've seen this terminology. We have two types of hypotheses. There's a null and an alternative. The null is the hypotheses we'd like to nullify or to reject, and I write it as H0 for null, and in this case I use Greek letters mu. So mu is a symbol for the mean or the average. So the average, and we use Greek letters when we're talking about population values, and we use Latin letters like S or M when we're talking about sample values, and we collect samples. We don't deal with the population, but our intent is to generalize our findings to the population. So in this case, I have mu of group 1 is equal to mu of group 2(1). An alternative, there is no difference between, well, there's several different alternatives we could have. One is that there is a difference between the treatment and control group. And what we could say there is, in this case, that there is a difference, but we're not stating in which direction the difference is. In this case, we're saying there is a difference, and the mean of group 1 is going to be greater than the mean of group 2-1, or the mean of group 1 is less than the group of 2-1. We'll talk about this in stats more, but these are important distinctions to make in terms of your study's power. Power is the ability to reject a false null hypothesis. We'll talk about that later. You select your research design. If you're doing, you'd ideally want a randomized controlled trial, but you can't always do that. So if you're testing a new drug, you'd want to do a randomized controlled trial, randomly assigning individuals to the experimental and the control group. Sometimes you can't do that for ethical reasons, so that we saw there are other study designs that you could use, like a case control study, or sometimes you can use natural experiments, like individuals who are exposed to some toxin because of where they live may differ from individuals who are not exposed to that toxin, but we can't forcefully expose people to the toxin to see what happens. If we're doing a randomized controlled trial, really the best way to do any study is what we call a mixed design, where we have both within and between group effects. Within means when we have, this is a change within an individual, so this means a repeated measure. So for instance, if we wanted to test the effect of the drug on happiness, we'd measure happiness at pretest, we'd give the individuals the drug or the placebo, and then we'd measure happiness again. So we're measuring it twice. So we want to see if there's a change within that individual. That's called a within design. And then the between is between the different groups, drug versus placebo. So ideally we want to do both, right? So we'll actually test for an interaction, a time by treatment interaction. You want to define your ideal participants based on inclusion and exclusion criteria. This is a very complicated topic because not everybody should be included in your study. So if you're testing, say, the effects of a drug and depression, we probably want to eliminate people who have other comorbid conditions that could interfere or confound your study. It could be confounding variable. And like, who do you want to include? So you have to identify that. You want to identify the number of participants or sample size. We do that in something called a power analysis, where we calculate the sample size. You'll learn about that in stats. Generate your recruitment strategy. How will you recruit participants? Sometimes you can just recruit them through hospitals because you have the data available to you. There are databases of participants with particular conditions. That can be problematic too, because you introduce other issues, like for instance, your participants may not be reflective of the population as a whole because they're already hospitalized individuals. So that causes you to have, while you may have internal validity, you have less external validity. That means being able to generalize your findings to the population at large. Prepare your institutional review board applications. We have to make sure that we get IRB approval when we do any study. You can't just do a study. You can't, oh, you don't want to do the study. You can't do that. You have to always get IRB approval. So this is to make sure that what you're doing is ethical and there's no harm to the patient in any way, and the participant has an opportunity, and this we call informed consent, to reject participation in the study. Heck, I don't want to be in this study. We saw this in the most famous case in the U.S. is the Tuskegee syphilis study, where, and I can't remember the number right now, but a large number of African American males were not given treatment for syphilis, and the researchers were part of the public health service or at the time, and they actually wanted to know what the natural history of syphilis was, so they decided to deny treatment to these black males. So that was a very unfortunate part of our history, but the point is that they didn't give these individuals an opportunity to reject participation. Some of them may have wanted to participate, but very doubtful when you have medication available and your life could be on the line. So I doubt people would have wanted to participate and say, hey, I'll deny myself treatment. But you have to give the opportunity to the person to make that informed choice. That's an extremely complicated topic, and when people cannot make choices, we have to find a proxy. Like children cannot make choices for themselves, we need their parents to make the decision. Or people with certain kind of impairments cannot make a choice, or if they don't speak the language, so you always have to have a proxy available. But you have to get IRB approval. So let's see, prepare a data collection strategy. Again, this is complicated in itself. If you're looking for a random sample, you have to use some kind of a randomization strategy. There's tons of those available freely online. By the way, randomization makes sure that all participants have an equal chance of being selected. The whole population of interest has an equal chance of being, each individual within the population has an equal chance of being selected into the study. You identify the best strategy for randomization to the different levels. So there's both, so that there's random sampling and random assignment. So we have to assign individuals to the different levels of the treatment, right? And we want to make sure that the groups are as similar as possible in terms of demographic characteristics. And this is actually a complicated topic. And my current chapter of that I'm writing right now in my research methods textbooks talks about this in detail, and I'm not going to talk about it here. You are taking research methods, so that'll be discussed there. All right, so one thing that I'd like you to do is I'm giving you this assignment, and in this assignment I'm having you, and you'll see this of course uploaded on the course. You could complete this for your own practice and also for extra credit as is needed for the course. Some of you may not do well on the mathematical part of this course, so I'll give you this opportunity. So it's a fictitious grant. Grants are applications to provide money to conduct studies. So I created this fictitious grant. I want you to answer every single one of these questions here. You should be able to do this based on what we've talked about in this course. You might have to look up some stuff, do the best that you can, like type 1 error rate. This is something called alpha, and you should have had stats before, because I know everybody in the program has had stats, so you should be able to answer this or look it up if you don't know. Just know power should be at least at a minimum 0.8. That's a 80% chance of rejecting a false null hypothesis. Again, you should know most of this stuff. You may not know things like D, but D is an effect size. In order to determine our power, we have to expect some kind of effect of our treatment on our outcome. This is also known as Cohen's D, and this value is a difference between the mean of, say, two groups, right? Of two different groups divided by the standard deviation of that group. This is a pooled standard deviation, right? So it's pooled from two different groups. And this is an R value. R is a correlation coefficient. It's also used as a measure of effect. And here are some heuristics for these. So at least you should know, well, I'm expecting to see a medium effect, or I'm expecting to see a small or a large effect. We'll talk about this more in statistics, but generally when you're planning a study, you have to be very accurate in which of these effects you think are going to happen. You better have a lot of evidence if you're proposing a large effect. Medium or small effects are more likely. Small effect means you're going to need a very large sample size. So just keep that in mind. Recruitment, talk about IRB, data collection. So this is not an assignment for grading, but it could get you extra credit, and it'll help you understand the material better. All right? Thank you, everybody, and have a wonderful week.